my name is NanaYorke, and I'm currently a sophomore at Marquette University High School. And I did my presentation on electromagnetic radiation. Most people commonly know as the main part of it is light. So I tried to stylize my board in a way that kind of reflects the entire spectrum, so it goes from blue to green, then yellow, then orange, and then finally red, which is the way that our light spectrum works. So we're going to start with gamma rays, which have the shortest wavelengths, and because they have the shortest wavelengths, they are also the most energetic in their movements, which causes them to be the most harmful. So here we have a diagram of visible light photons as well as gamma ray photons, and it shows the difference in how visible light is not as erratic in its movement compared to gamma ray photons, and because of this is what causes them to be so harmful. The frequency of how the photons are moving. If it hits you multiple times, you're going to take damage from it. And here it also shows gamma ray bursts. And gamma ray bursts release a ton of energy. In fact, they can release in 10 seconds more energy than the sun can in its entire 10 billion year lifetime. So it's a ton of energy. Next we have X-rays, which are used for a whole lot of things. Mostly we're used in the medical field, and the fact that dentists and doctors use them to look at injuries. And scientists and astronomers actually use them more for searching for elements on different planets. For example, we have a graph here that looks for the hydrogen on Mars. As you can see, the red is where there's the least and blue is where there's the most. And next on the shorter waves list we have ultraviolet light, which is less damaging than gamma rays, but is still dangerous and typically can cause skin cancer if you're exposed to light from the sun too long, which actually emits ultraviolet light. So ultraviolet light is interesting for a couple of reasons. One, bees actually see in ultraviolet light, while we see in visible light, as you probably know. And this is interesting because it allows for bees and other insects who actually can also see in UV to see flowers and plants in different ways than we can. So they're basically seeing in a whole different spectrum than us. But we, as astronomers or scientists, use them to look at temperature on different objects. For example, this is almost the same picture. These are both pictures of the sun, one in X-ray and then one in UV. In the one in UV, you can see that the blue and green is where it is the hottest, and the orange and yellow is where it is the coldest. But X-ray actually just shows the elemental properties of it compared to the UV. Next we have the longer waves, which are the ones that most people are more well known with, and also the ones that are less damaging. So we have microwaves, which they can still cause damage to you, but they're less likely compared to gamma rays. We use microwaves obviously to cook our food, but astronomers also, actually meteorologists use them the most for weather, and we use it to look at hurricanes and such, mostly because they are not affected by the weather as much as other kinds of waves and light. And it's mostly because they can look at them without having to worry about that, essentially. And next we have visible light, which we all know about probably, as you can see it. And it's important for the two properties of reflection and refraction. And this is one, how we know that light is made up of photons, as well as being waves, and it's because of their ability to bend and refract is how we know that. The reflecting is the most obvious one when light bounces back towards you, and then refracting is where light is being bent and slowed down, which allows you to see the different wavelengths as well as the different colors of light, which are made up by the different wavelengths. And finally, we have radio waves, which are the largest of the wavelengths, the least harmful. It's probably why we use them in radio so much. Since they're so huge, they're easy to transmit and are able to travel farther distances at an easier way. And that's why we use them in AM and FM radios. However, AM is less quality because the wavelengths are larger. They're the ones that tend to be the sizes of planets, whereas FM is closer to the size of a football field. And astronomers use them in telescopes to look for any object that may emit radio waves, and that's how they can detect it. And finally, I brought a question called the Olber's paradox, which basically asks the question of why is it that, despite the fact that there are so many stars and objects that emit light in space, is space so dark? And it's a question that probably a lot of people have thought of, but just didn't bother to look it up or ask about it. And the generally accepted answer is that since everything in the universe is constantly moving, thanks to what happened in the Big Bang and everything, the wavelengths of the light that's emitted from any object becomes longer and longer. And as you can see, once you get to a certain point, you can't see you can't see the actual light anymore. It becomes longer and longer, so you can't see it. And that's basically what happens to every single kind of light that is emitted from anything. For example, the sun. It only takes light 8 minutes to reach us from the sun, but we can't see any of the light in between. We can only see it once it hits the Earth, which is what slows it back, kind of slows it back down to the smaller wavelengths. So that is the presentation. Are there any questions?